All right, number 18, given that for x greater than or equal to, find dy dx at the point 1, 1. Okay, so we have the derivative of e is itself, and then we have to multiply by the derivative of the exponent because of chain rule. So we've got the first times the derivative of the second plus the derivative of the first, which is 1, times the second. And then we have a chain rule again. So the first times the derivative of the second plus the derivative of the first times the second. And then we have equals e, which is just a number. So that's 0. All right, so now we need to sub in 1 for x and y. So we'll have e to the 1 times 1 times y prime plus 1 minus 1 squared times 1 over 1, which is just 1, plus 2 times 1 y prime natural log 1, which is 0. Okay, equals 0, so that goes away. So we're going to have e times y prime plus 1 minus 1 equals 0. So now we will add 1, divide by e, and then subtract 1. 1 over e minus 1. All right, so we have this curve, find dy dx. So we've got 3x squared plus 2y, y prime, equals first times the derivative of the second plus the derivative of the first, which is 1, times the second. And then we have to solve for y prime. So we'll get 3x squared minus y equals x y prime minus 2y y prime. And then we factor out a y prime, which is x minus 2y, and then divide. So we have 3x squared minus y over x minus 2y. Find the coordinates of the point on the curve where the tangent line is parallel to the x-axis. So x-axis means the gradient is 0. So we will set our derivative function equal to 0. Cross multiply by the denominator. So we've got 3x squared equals y. So then we can, because we need the coordinates of the point on the curve, so we can substitute this back into our curve. So we're going to have x cubed plus y squared equals x times y. So this is x cubed plus 9x4 equals 3x cubed. So we're going to have 9x4 and then minus 2x cubed equals 0. Factor out an x cubed, and then we're going to have 9x minus 2. X cubed is 0, so x would be 0, but x can't be 0. So this one gives 2/9. So then we would substitute it back in to the curve. So we're going to have 2/9 cubed plus y squared equals 2/9 y. So that's 8 over 729 plus y squared equals 2 over 9y. So we have quadratic y squared minus 2/9 y plus 8 over 729 equals 0. And when you put this in on the polynomial solver, you're going to get that y is either 2 over 27 or y is 4 over 27. So we have 2/9, 2 over 27, 2/9, 4 over 27. So those are the points on the curve where the tangent is parallel to the x-axis. So now if we want it parallel to the y-axis, we have 3x squared minus y over x minus 2y is going to be undefined. So we want x minus 2y, the denominator, to equal 0. So x will be 2y. If we sub this into the curve, that is 2y cubed plus y squared equals 2y times y squared. Okay, so now we're going to have 8y cubed, subtract the 2y squared, so minus y squared equals 0. Factor out y squared, and this is 8y minus 1. So again, y can't be 0. So y has to be 1 over 8. So this time, because basically I did this last time because it's a point on the curve. But because we have basically simultaneous equations, we can just substitute it into here, even though it's part of the derivative. So you'd think it gives you, you know, the grade, like 1 over 8 is the gradient for this x, but it's just part of our simultaneous equation. Okay, so we've got x is going to be 2 times 1 over 8, which is 1/4. So our other point is the point that is tangent. No, the tangent at this point is parallel to the y-axis is going to be 1/4, 1/8. So yeah, this one where you have 3x squared equals y, you can do 3 times x is 2/9 squared equals y. So this one's going to give you 3 times 4 over 81, and this is the 27. So I'm going to check the graph for this point rather. So you can see that this black point here is the one that's parallel to the x-axis, the tangent is. The red point is parallel to the y-axis, its tangent. But the blue point is just an extraneous solution. So just use your, your, like the thing you got from the gradient. So this one is not an answer, okay? All right, so this is, if y equals that, show dy dx is that. Okay, so this is one of those ones where it's like a method to remember kind of thing. So since we see e to the y-ish over there, we can do e to both sides, okay? So we're going to have e to the y, and then e to the natural log goes away. So we're going to have this. Now, if we do the derivative of each side, we're going to have just e to the y times y prime equals, and then the derivative of this side is 1/3 e to the negative 2x times negative 2. So now we have y prime equals negative 2/3 e to the negative 2x over e to the y. Okay, so if we look where we're going, we need this all in terms of y. So we need this e to the negative 2x away. So we have a relationship here between e to the y and e to the negative 2x. So we're going to have 3e to the y equals 1 plus e to the negative 2x. So we can subtract 1 and now substitute. So we're going to have negative 2 over 3 e to the negative 2x is 3e to the y minus 1 over e to the y. So now, let's distribute. So we're going to have negative 2e to the y plus 2 over 3 over e to the y. So each thing is over e to the y. So we're going to have negative 2 plus 2 over 3 e to the y, which I'm going to write as e to the negative y up here. So if we take out, they wanted 2/3 out. So we're dividing all this stuff by 2/3. So 2/3, this is just going to be e to the negative y. And then negative 2, so this one is e to the negative y. And if we do negative 2 divided by 2/3, that's negative 2 times 3 over 2, which is negative 3. Okay? All right, so 21, find the gradient of the curve of that. Okay, so we want the derivative here. And then we have to multiply by the derivative of the inside function, which is the first times the derivative of the second plus the derivative of the first times the second, and that's equal to 0. So if we now, so let's find out our x when y is 1/2. So we have 2 sine x over 2 equals 1. So sine x over 2 is 1/2. So if we divide by 2 our domain, we're going to have x over 2, sine is 1/2 at pi over 6. So in between pi over 2 and pi, that's over here. So that's 5 pi over 6. So we're going to have that x is equal to 5 pi over 3. So now we can substitute in the derivative 2 cosine 5 pi over 3 times 1/2 times 5 pi over 3y prime plus 1/2. And that's equal to 0. So if I divide by 2, that goes away. And then we're going to have 5 pi over 6 here. And this bit. So cosine 5 pi over 6, that is going to be root 3 over 2 negative. It doesn't really matter because we're going to divide it away anyways. So, yeah, now dividing by that goes away. So 5 pi y prime over 3 plus 1/2 equals 0. So if we subtract 1/2 and then multiply by 3 over 5 pi, we're going to have negative 3 over 10 pi is the gradient of the curve. All right, so take the logarithm of both sides and then use implicit differentiation to find the derivative of the function y equals x to the x in terms of x. All right, so if we take the natural log of y and the natural log of x to the x comes down, and now we want to take the derivative. So we're going to have 1 over y prime equals first times the derivative of the second plus the derivative of the first times the second. And we just have, so y prime multiplying by y, x times 1 over x is 1 plus natural log x, and y is x to the x. So we're going to have y prime equals x to the x, 1 plus natural log x. So that's the derivative of that function in terms of x. So again, we're taking the log So this is 1 over y prime. First times the derivative of the second, chain rule, plus the derivative of the first times the second. So we're going to have y prime equals y times all of this. Through x squared. Okay, plus natural log x squared plus 1. And then we have that y is x squared plus 1 to the x, 2x squared over x squared plus 1 plus natural log x squared plus 1. And that's that. 24, same thing. Natural log y equals x squared plus 1 natural log x. 1 over y prime equals the first times the derivative of the second plus the derivative of the first times the second, multiplying by y, but y is x to the x squared plus 1. And then we have this. Given the derivative of f is known, use this property to show the derivative of its inverse function. The arc sine is that. Okay, so if we do, all right, so if we have sine y is x, when we do the sine of this side and the sine of this side, so we want to get to dy dx, so we can start with this. So dx, the derivative of x with respect to y is this. And then, this is going to be cosine y, right? So then we can do this to the -1, which is going to be dy dx is 1 over cosine y. And we know, so we want this, and this is, remember, cosine squared y plus sine squared y is 1. So this is 1 over 1 minus sine squared y. And we know sine y is x. So this is 1 minus x squared. Oh yeah, I forgot the square root here. So that's that. Okay, very similar to this one. So we will do cosine y equals x. So then we do dx dy is negative sine y. And then we flip it to the -1. So we're going to have 1 over negative sine y is dy dx. And then from this here, we're going to have 1 over negative the square root of 1 minus cosine squared y. And we know that this is equal to x. Oops, sorry. -1 over 1 minus x squared. All right, use the quotient rule to show the derivative of tangent is secant squared. So, quotient rule. So if we have y equals tangent x, that's sine over cosine. So we have the derivative is going to be cosine squared on the bottom, cosine times the derivative of sine, which is cosine, minus sine times the derivative of cosine. So this is v u prime minus u v prime over v squared. Okay, so we're going to have cosine squared x plus sine squared x over cosine squared x, which is 1 over cosine squared x, which is secant squared x. Hence, by using this, all right, so we're going to have y is arctan x. So tan y equals x. So if we want dx dy, this is going to be secant squared y. And that, in the formula booklet, is 1 plus tangent squared y. So if we do to the negative 1 here, we're going to have dy dx is equal to 1 over 1 plus tangent squared y. And we have that tangent y is x. So we know that we have 1 over 1 plus x squared.